Okay, it's 7:30. Welcome, guys. This is the review for Chem 2. My name is Imani, so I'll start now. All right. The first question says rank the following compounds in order of increasing vapor pressure. Vapor pressure increases with the smallest intermolecular force. So, okay. So high vapor pressure. LD stands for London dispersion. So London dispersion forces are going to have the highest. And then dipole-dipole. And then the hydrogen bond. So we have CCl4, CH3, NH2, and HCl. So CCl4 has 4 polar bonds, carbon being the partial positive, and then chlorine having the partial negatives. So these are all polar bonds, but they're going to cancel out. So this is London dispersion. Then we have CH3NH2. And then the end is bonded to 2 hydrogens, so this is a hydrogen bond. Then we have HCl. 8 hydrogen having the partial positive, so it goes this way, so this is dipole-dipole. Number 1 is C. Wait. Number 1 is D? Yeah. All right. Now number 2 says to rank the following compounds in order of increasing boiling point. So boiling point is the opposite of vapor pressure. So that means the hydrogen bond is going to have the highest boiling point, and then dipole-dipole, and then London dispersion. So you have CO2, HF, and CH3 nitrogen. So HF, again, like HCl, partial positive is on the hydrogen. And then this is a hydrogen bonding to a fluorine, so this is a hydrogen bond. Then we have CO2. So again, these are polar bonds, but because they go out this way, they cancel out. So this is London dispersion, even though these 2 bonds right here are both polar. And then we have CH3N. So we have N. So even though there's nitrogen and hydrogen, they're not directly bonded to each other. So this isn't hydrogen bonding, this is just dipole-dipole. That means the answer should be A. All right. Number 3 says how much energy is required to vaporize 23.55 grams of water at its boiling point. And then I gave you the heat evaporation for water. So this equation is Q equals N delta H. N stands for the moles of whatever the compound is. So to find the moles, we're going to do the grams of water, which I told you guys is 23.55. And then we're going to divide by the mole mass of water, which is 18. Then times the heat evaporization. So we get 53.2. And that's A. Now 4 is a phase diagram, and I ask which transition represents a solid to a gas. So when you're given a phase diagram, I would just automatically label the solid, liquid, and gas. So you know C is a solid because it's the closest, it has the lowest temperature, and then high pressure. So then B is liquid because it's in the middle, and A is gas because it has all the temperatures, and it's having the highest over there. So this says a solid to a gas, so that should be C to A. All right. Number 5. We're going to find the specific heat of platinum. So in this problem, you're given, so this is Q equals MCAT. M being the mass, C is the specific heat, and then delta T is the change in temperature. So we're trying to find the specific heat of platinum, and we're giving everything else for water. So we're going to use the energy required to change water to that temperature to find the specific heat of platinum. So it's basically Q equals MCAT, and then you can write MCAT twice. So the mass of water is 130. Specific heat of water is 4.184. Change of temperature for water is 27. The mass of platinum is 62. The change of temperature for platinum is 33. All right. So we're going to figure out the left side. Simple out the right side. And you should get 0.7. Oh, sorry.
So the change in temperature is the final minus initial?
Yes.
Wouldn't that be negative 33?
It doesn't matter if it's negative or not. It's just the absolute value of change in temperature. So we should get 0.7. All right. Anybody have any questions on the 5 questions I just did?
I have a question, actually.
Shoot.
What was number 1 again? Vapor pressure, what?
The answer is D.
But how come vapor pressure increases as like intermolecular forces decrease? Is that again?
Vapor pressure is basically the amount of gas in a closed solution. You need energy for the liquid to turn into a gas. So that means the particles in the liquid need to be able to break that barrier on the surface. So if the forces are stronger, there's going to be less vapor pressure.
So vapor pressure increases as intermolecular forces decrease?
Yes.
Thank you.
Yep. Now we're going to go on to 6. All right. So we're looking for the radius of copper. So for this one, you need to know the edge length for a face-centered cubic. Okay. All right. So the equation for the edge length for a face-centered cubic is 2 root 2 times the radius. So in this problem, we're given the edge length and we're looking for the radius. So we're just going to set it equal to this. So we're going to have 351 equals 2 root 2 times r. So we're just going to divide by 2 root 2. We're going to have what r is.
Answer 5 again.
See?
C. K.
So we should get the radius equals 124. All right. Now in 7, we're looking for the mass of nickel. So for this one, we need to know the atoms per unit cell in the face center cubic, and then we're going to need the molar mass for nickel. All right. So the atoms per unit cell in the face center cubic is 2. It's going to have 2 times the molar mass of nickel, which is 58.7. And then we're going to divide it by Avogadro's number to get the mass. So and we should get 1.9 times 10 to the negative 22. So 7 is A. Any question on those two questions? Yes. Remember in that chart for the solids, it tells you atoms per unit cell, and at face center, the atoms per unit cell is 2.
What is number 5 again?
5 is C. I have the answer key up in the document I uploaded.
But I got like, so 6 is A,
Yes.
and how did we get like 07?
How did we get what?
How did we get 07?
0.7 for 5?
Yeah,
You just divide.
I got like 7 points.
It should be 0.7. Could be a calculation error.
I don't know. Should we have divided something or
Yes.
like?
Whatever I wrote. Yeah.
No.
Okay. So we're going to go to 8. So this has to do with solubility of solids and gases. So as the temperature increases, the solubility of a solid should increase, and that should be the opposite for a gas. So we have potassium chloride, which is the solid, and carbon dioxide, which is the gas. And we're increasing the temperature. That means carbon dioxide should bubble out, and then the potassium chloride should be more soluble. The only answer that makes sense for that one is B. All right, now number 9, I put a typo. It should be 22.4, not 24.4.
I think you made a typo number 5.
Did anybody else get a different answer for number 5? Yes? You got 7.1? Everyone else got 7.1?
Yeah, 7.1.
Then it should be 7.1.
Shoot.
All right,
It's 7.2 actually. Yeah.
close enough. Okay. So now we're going to do 9. We're looking for the molality. The equation for molality is M equals moles of solute divided by the kilograms of the solvent.
Is it 7.1 for 5?
So now we're given the grams for glucose and the liters of water, and we're given the density of water. So the first part is we're going to find the moles of glucose. So the mass is 22.4, and divided by the molar mass of glucose, which is, I believe, 180. So we get 0.068 for the moles of glucose, and now we're going to find the kilograms of the solvent, which is water. So we said the density of water is 1 grams over milliliters. So we're going to need to cross out the milliliters here. We were told that it was in 0.5 liters. So we're just going to change that 0.5 liters to milliliters. So we're going to times 0.5 by 1,000 times by 500 milliliters. So it's going to cross out. I'm going to have 500 grams. And then we need to change the grams to kilograms. So we're just going to divide by 1,000 to end up with 0.5 again.
Excuse me. It's actually 24.4 grams of glucose.
Yeah, I said I made a typo. It should be 22.4. If you do 24.4, you don't get any of the answer choices. Because it was typo.
So it's actually 1.35 moles, right?
For what? Yes.
Number 9.
All right, so we're looking for molality. Molality is moles over kilograms, right? So we need to find the moles of the solute, which is glucose. I told you that the grams of glucose is 22.4. Molar mass of glucose is 180. So grams divided by molar mass, we get moles 0.068. Following? All right. So we have the moles, and we have a question?
I got 0.12.
For moles? Okay. 0.124. So you have 0.124 divided by 0.5. So we get 0.248, which is C. All right. Everybody good on that one?
Okay.
Now we're going to go on to 10. So this one, I gave you the percent of sodium nitrate and the density of it, and we're going to find the molarity of it in the solution.
Excuse me.
Yep.
By calculating 24.4 grams.
It's 22.4.
22. Made a typo.
Yep, that's what I said.
It's 22.4 grams, right?
Yep.
Oh. 22. I'm sorry.
All right. So I said sodium nitrate is 12.5% by mass. We're looking for molarity. So molarity equals moles over liters. All right. So we're going to find the moles of sodium nitrate by figuring out what the mass of sodium nitrate is. So it's 12.5% by mass. So we can use any mass we want for this problem as long as the sodium nitrate is 12.5 of it. So we're going to say this solution is 100 grams. I'm going to say sodium nitrate of that is 12.5. So when we divide that, that's 12.5%, right? Everybody following what I just did? Yep. Okay. So we're going to say sodium nitrate is 12.5 grams, and then we're going to divide that by the mole mass of sodium nitrate to get the moles. The mass of sodium nitrate is 85. You guys know how to find the molar mass, right? I don't need to go over that? Okay. So then we should get 0.147 moles. So we have the first part, and now we're going to find the liters. So I told you that the density of sodium nitrate is 1.02 grams per milliliters, but we're looking for liters here. So we're going to flip this over 1.02. So milliliters is on top and grams is on bottom. And then 1 over 1.02 is 0.98. So this equals 0.98 milliliters over grams. All right. And then we said this solution is in 100 grams. So we're going to times it by 100 to get rid of the grams here. Following? Okay. But now it's still in, just move the decimal place over 2 points, but now it's still in grams. So now we're going to divide it by 1,000 to get kilograms.
How do we determine like the moles of milliliters per grams?
How do you find the moles part?
No, the 1.02 grams per milliliter.
I gave you that. That's the density that I gave you in the problem.
Okay. How do we like determine grams?
So we said this is 12.5% by mass. That means it doesn't matter what this number is, as long as it's 12.5% of the total solution. So we're going to say the total solution is 100, and the mass of sodium nitrate is 12.5. So it doesn't matter what number you use, as long as the solute ends up being whatever percent they give you. Okay. So 0.098 liters. So now we have everything we need to find this one. So 0.147 divided by 0.098. We should get 1.5.
Thank you, Imani.
Yeah. Thanks. Okay. Now we're going to move on to 11. So this is the equation we're going to use. I forgot to give you guys the KF, but they would give it to you. And the KF depends on what the compound is. And in this situation, it's water. So the KF for water is 1.86. We're trying to find the grams, which we need that to figure out the molality. So I'm just going to leave it as M. The I in this situation is 1, because we're talking about glucose. And I is a Van't Hoff factor, because glucose isn't an electrolyte, it's just 1. And the delta T for this one should be 4.2, because the freezing point of water is 0. So the delta T in this situation is 4.2. So now we're just going to divide to figure out what m would be in this situation. So we get m equals 2.258. Now we have the molality, and we're going to use this to figure out what the grams is. So molality equals moles over kilograms. We were given the kilograms already. Yeah, 2.2 equals moles over kilograms, which we said is 10. So we're going to times both sides by 10. We get 22.58 equals moles. And moles is grams divided by molar mass, right? So it should be 22.58 equals the grams, which you don't know yet, divided by the molar mass of glucose. Oh, you can't see? Sorry. The mass of glucose is 180. So now we're going to times everything by 180. Then we get 4,064.5 grams. But I give the answer in kilograms, so we're going to divide this whole thing by 1,000.
How come we get 22.58?
Multiplied by 10, which is the kilograms of the solvent.
That's the molality.
What?
The molality, do we multiply the molality times 10?
Yes.
I didn't get it. Now I do.
Okay. So for kilograms of the solution, we get 4. So the answer is B. All
I
right.
had no idea.
Now 12. This talks about the Van Hoff factor. So basically, if it's a non-electrolyte, the Van Hoff factor is 1. But if it's an electrolyte, the Van Hoff factor is just how many particles it breaks up into water. So this right here is glucose. The Van Hoff factor is 1. KNO3 is going to split up into 2 particles. Splits up into the potassium and then the nitrate. And then calcium nitrate splits up into 3. 1 of the calcium and then 2 of the nitrate. So the answer should be C. It's going to have the highest boiling point. Since it breaks up into 3 particles, it's going to increase the boiling point of whatever it's in. Anybody have questions on whatever we just did? Yes? Yeah. It doesn't matter because it's changed the temperature. So like if it's in Kelvin or Celsius, the change temperature should be exactly the same. Yes? So for this equation, that little m is molality, and molality is moles over kilograms. So we need to find the grams of glucose. So we're going to find that by using the moles over kilograms. Still lost? Yes. You want me to go over the whole problem again? Up to, so you're up to right here? Okay. So molality is moles over kilograms. We found out what molarity equals, which is this 2.258. In the problem, I told you that the solvent is 10 kilograms, so that's where this 10 comes from. So we multiply both sides by 10, and we get 22.58 equals the moles, and the moles is grams divided by molar mass. So it's 22.58 equals X, the grams we don't know yet, divided by the molar mass, which is 180. Yes?
Couldn't we get like, if we got like a molarity of 2.258 moles, why do we have to multiply it times 10?
This problem didn't ask for the molality. It asked for the mass of glucose.
Okay. Let me recheck that.
Okay, everybody good?
Yeah.
Okay. Okay, so now we're going to go on to chapter 14. All right. So I gave you a reaction. So this has to do with rate law. So when we double the concentration of nitrogen dioxide, it quadruples the rate of the reaction. That means nitrogen dioxide is second order. Then when we double the concentration of both the reactants, the rate of the reaction increasing by a factor of 4. So that means when we double the concentration of fluorine, it didn't change the rate at all. So that means fluorine must be 0 order. So NO2 is second order and fluorine is 0 order. So it should be C. Yes? Okay. So for this reaction, we said doubling the concentration of NO2 quadruples the rate of the reaction. So that means second order. And then we double the concentration of both of them, and the rate of the reaction is still quadruple. So that means when we doubled the rate of F2, that didn't affect the rate of the reaction at all. So that means it must be 0 order. Okay. 14 is pretty much a definition question. In that chart in the book, they fit the line for 0, first, and second order. So this question is just asking for what's the straight line for first order, and that's C. So when you do the ln of the substrate of the concentration, you're going to get a straight line for first order. Now we're going to use a chart I gave you guys to figure out 15 and 16. For 15, we're going to figure out the rate law of this reaction. All right, so to do this, we know the rate is going to equal K times concentration of NO2, which we don't know yet, and then times concentration of F2, which we also don't know yet. So to figure this out, we're going to look at 2 sets of this reaction and then figure out the rate order for both of them. So we're going to pick the first and the second to find the order for NO2. All right. So the initial rate of the reaction is 0.051 equals K, which is concentration of NO2, which is 0.2, X times concentration of F2, which is 0.1. And the second reaction we're looking at is the first one. So the initial rate is 0.026 equals K. Concentration of NO2 is 0.1. And the concentration of F is also 0.1. So I'm going to cancel out the K's. I'm going to cancel out F2 because concentration is exactly the same, so the order doesn't matter yet. Now we're going to divide 0.051 by this, and we don't get exactly 2, we get approximately 2, which is close enough. So 2 equals 0.2 divided by 0.1, which is 2. So you get 2 equals 2x. That means x is 1. So we know NO2 is first order. All right. Now we're going to do the same thing for F. But as you can see, none of the concentrations of NO2 are exactly the same for any of these sets of reactions. But that's okay, because you already know what the order of NO2 is. So we can pick any 2 plots we want to figure out the rate for F. So we're going to do the third and the second one. All right, so the rate of the third one is 0.103, and that equals K. Concentration of NO2 is 0.2. Concentration of F is also 0.2. Then we're going to divide that by 0.051, which equals K. Concentration of NO2 is 0.2. And concentration of F is 0.1. We're going to cross out K. We're going to cross out the 0.2. Then we're going to do 0.103 divided by 0.051, which is again approximately 2. And then we get 0.2 divided by 0.1, which is 2. That means Y is 1. So that means F2 is also first order. So that means the rate of this reaction should be C. Okay. Now 16 asks for the rate constant of the reaction. Now to figure this out, we're just going to look at one set of data. We're going to figure out what K is, since we already know the rate order for the two reactants. So we're going to pick the first one. So the rate for the first one is 0.026 equals K. Concentration of NO2 is 0.1. We said NO2 is first order. Concentration of F2 is also 0.1, and it's also first order. So now we do 0.1 times 0.1, so you get 0.01. And now we're just going to divide by that to figure out what K is. So you should get K equals 2.6. 16 is D. Which one, 16?
Yeah.
Okay. So for this one, we're just looking for the rate constant. So because we already know the rate order for the, if I'm talking too fast, you can tell me to slow down. I know I talk fast sometimes, so. So we're going to look at any set of data. It doesn't matter which one you look at because you already know the order for all of them. So I just chose the first one. The initial rate for the first one is 0.026. So 0.026 equals K times concentration of NO2 and F2, which are both 0.1, and they're both first order. So we multiplied 0.1 times 0.1, and you get 0.01. And then we're looking for K, so we're just going to do 0.026 divided by 0.01. And you should get 2.6. Okay. 17 is just the definition of a catalyst. So a catalyst decreases the activation energy. So the only one that says anything about activation energy is C. So a catalyst reduces the activation energy of reaction and increases the rate of the reaction. Okay. Does anybody have any questions on the stuff I just did for chapter 14? Nope. Okay. Now we're going to go to 15. So for this one, we're looking for the Kc of the reaction. And remember, K is products over reactants, but we don't include solids or liquids. So that means for the K for this reaction, we're not going to look at the reactant half because it's a solid. So that means the K of this reaction should just be NH3 times H2S. So the answer is D. Okay. Now 19, we're looking for the concentration of one of the products. So we're going to do an ice table. All right. So initially, there's 0.55 of CO and H2O. Nothing was told about the products, so we can say initially there's nothing of the products yet. The change for both the reactants should be negative X, because we don't know what the change is yet. And the change for the products should be positive X. So that means at equilibrium, the concentration of the products are both X. At equilibrium, the concentration of both the reactants is 0.55 minus X. Okay. So that means at equilibrium, the K for this problem is going to be the concentration of CO2 times concentration of H2 over the initial concentration of CO minus X and the initial concentration of H2O minus X. Now we're just going to plug stuff in. So the Kc for this reaction at 500 Kelvin is 64. So 64 equals concentration of CO2 and H2. They're both X, so we're going to get X squared. Initial concentration for both of them is 0.55. So we're going to have 0.55 minus x squared. Now we can square root every, is that better? Now we can square root everything. So square root 64 is 8. So 8 equals x divided by 0.55 minus x. So now we're going to multiply the 0.55 minus x times the 8. So you get 4.4 minus 8x equals x. So now we're going to add the 8x to the other side, and we're going to get 4.4 equals 9x. And then 4.4 divided by 9 is 0.48. So we get B. Everybody good on? Yeah, yeah. Good? I'm going to the next one. Okay. Now, 20 says, which of these situations will increasing the pressure have no effect in the amount of substance present in the equilibrium? So this has to do with when you increase the pressure, we're looking at moles of gas, but nothing's going to happen when the moles of gas are exactly the same on both sides. So we're going to look for one where the moles of gas are the same. So for A, moles of gas on the left is 3, moles of gas on the right is 2, so it's not A. For B, the moles of gas on the left is 2, moles of gas on the right is 2, so the answer is B. Everybody good on that one?
Increasing pressure.
Okay. 21 is just a definition question. So equilibrium is the equilibrium is when the rate of the product's form equals the rate of the reactants used. So remember, at equilibrium, it's not when the concentrations are equal, it's when the rates of the forward and the reverse reaction are equal. So the answer is D. All right. 22 says, which reaction characteristics will be affected by a change in temperature? So when you change the temperature, they're asking you if the equilibrium constant changes and if the equilibrium concentrations change. So they both change. Changing the temperature is the only one that will affect the equilibrium constant. So the answer is C. Everybody go to that one?
See again.
So temperature is the only one out of the factors that you guys go over that changes the equilibrium constant. So when we do problems like this, they always give you a K and they tell you at a certain temperature. That's because at a different temperature, the K is going to be different.
Temperature is the only thing that will affect equilibrium constant.
Okay. 23 says, what would be the effect of increasing the temperature of products that is known to undergo an exothermic reaction? So no matter if it's endergonic or exergonic, the rate of reaction is going to increase because it's the temperature is increasing, so the reaction is going to move on faster. Now we're going to increase the temperature, and exothermic reaction, the heat is on the product side. So that means when you add more heat, it should shift to the left. And the value of equilibrium constant should decrease. So 23 should be D. Yep. Everybody good on that one?
Yeah.
So now we're going to go to 16. So you're given the molarity of a solution, and we're looking for the Ka of a weak acid. Okay. So we weren't told what the weak acid is, but it doesn't matter because the reaction for any weak acid looks the same. So we're going to have HA, A standing for the acid, and it's going to be in a solution containing water. It's going to create H3O+. and the anion of the acid. Okay, so now we're going to do an ice table. So we aren't going to look at the H2O because H2O is a liquid, so it's not going to affect decay. So the concentration of this solution is 0.387, so that means initially there's 0.387 of this acid. This is before the reaction has gone along, so the concentration of the products should both be 0. Now the change for the acid should be negative x, the change for the products are both plus x. That means at equilibrium, the concentration of this acid is 0.387 minus x. All right. So the Ka for this weak acid should be concentration of H3O plus times concentration of A divided by the initial concentration of the acid minus x. All right. So we were given the concentration of H plus, which is the same thing as H3O plus. So that means this x right here is 1.6 times 10 to the negative 3. So because it's x squared, I'm just going to do 1.6 times 10 to the negative 3 squared over 0.387 minus 1.6 times 10 to the negative 3. When we do that, that'll give us the Ka.
Why is it squared?
So the Ka for this is H3O plus times A minus. So that's, we have it right here. That's x squared over 0.387 minus x. Okay. So when we solve this out, for the Ka, we get
Excuse me.
we should get B. Yeah.
Why is 1.6 times 10 to the negative 3 like concentration for H3O plus and A?
That's what's given in the question.
But that's H plus
H plus and H3O plus are the same thing.
and A minus.
What about it?
Is that the same as H3O plus?
No, but we know the concentration of H plus is x, so, and the concentration of A is also x. So that means these numbers are going to be exactly the same.
Okay. Thank you.
Mm-hmm. Okay. So for 24, did you guys get B?
Yeah.
Okay. I'm not sure why that one is bolded, but yeah, so it's B. 25 is just a definition question. So the ion product constant for water is H3O plus times the concentration of OH, which should equal 10 to the negative 14. So the answer should be A for 25. All right. Now 26, we're looking for the pH of a solution containing a strong base. So because the strong base, it's going to completely make all of those OH ions. But we're going to do 0.3 times 2, because this is strontium. We see there's a 2 here, so that means each time it's going to create 2 OH ions, not 1. You look confused. Following? So I'm going to do 0.3 times 2. So that means it creates 0.6 OH ions, not 0.3. So we're going to do the negative log of 0.6, and that's going to give us the POH, because this is the base. So when we do the negative log of 0.6, we get 0.22. Now to find the pH, we're just going to do 14 minus the POH. So we can do 14 minus 0.22. You should get 13.78. The answer is D. Okay. Now 27 says which of the following compounds is amphoteric. Oh, you have a question? Nope. Because it's a strong base, it's going to completely make that same amount of OH ions. So there's no need to. So you can make one and make it. You can't make an ice table because there would be nothing to make an ice table for. Yes.
Why do we have to multiply the concentration of O3 times 2 again?
So for each strontium OH ion, it makes, when it dissociates and reacts with water, it creates 2 OH, not 1 OH. So you need to multiply this number by 2.
Okay.
Okay. Now we're going to go on to 27. So amphoteric means that it acts as an acid and a base. So that means you need to be able to give away an H and receive an H. So HCl is a strong acid. So if it's a strong acid or a strong base, it's not going to want to act as the other one. So HCl is not going to want to act as a base, and it's not going to want to receive an H. Now NH4 can act as an acid, but it can't act as a base because it's not possible for it to gain any more H. It's full. So there's no more space on the nitrogen to receive an H, so it can't act as a base. It can't act as a base. Now HCl3, it has an H, so it can act as an acid, and there's a negative here, so we know it can receive one more H and become neutral. So this one acts as an acid and a base. Now D is an amphoteric because there's no H for it to give, so it can't act as an acid.
How do we get the K then?
Okay. 28 is a molar solubility problem. So looking for the molar solubility of AgBr in a solution containing 0.15 m NaBr. So to start this off, we're going to write how AgBr dissociates. Okay. So AgBr is a solid. It's going to dissociate into Ag and Br. So we're going to do basically an ice table. We're not going to focus on the solid portion because the K doesn't matter when we talk about solids. So initially, there is 0 of Ag, but there's 0.15 of Br because it's already 0.15 NaBr. Okay. So the change for both of these should be X. Oh, yeah, sorry. So at equilibrium, the concentration of Ag is X. The concentration of Br is 0.15 plus X. Now we were given the KSP, and it's 7.7 times 10 to the negative 13. And that equals X times 0.15 plus X. Because that's the concentration of Ag and Br at equilibrium. Now I want to cancel out the X because this K right here is really small. So if we're going to do 0.5 times X, you get 0.15 X equals the KSP. Now we're just going to divide to find out what X is. So we should get 5.1 times 10 to the negative 12. So that's D. Okay. Now 19, we have a buffer solution, and we're going to calculate the pH after adding 100 milliliters of HCl. So when you have a problem like this, we're going to look at the buffer, and we're going to look at the... Do you have a question? 27. See? Mm-hmm. So for 29, so we're going to add HCl. That means HCl is going to either react with HF or NaF. So acids react with bases. So that means HCl is going to react with NaF because NaF is the base in this reaction. Okay. So that means we're only going to focus on HCl and NaF, not HF. The first thing we're going to do is going to write the reaction out. So HCl and NaF, and we're not going to write the Cl portion because Cl is pH neutral, so it's not going to affect the pH of the solution. Same thing for Na. So HCl plus F minus is going to create HF and water. Okay. After we've done that, we're going to find the moles for both of these. So molarity equals moles over liters. This is a 1 liter solution, and the concentration of NaF is 0.25. That means the moles is also 0.25. Now we're going to find the moles for HCl. So the molarity of HCl is 1 equals X over 100 milliliters, which are going to convert to liters. So yeah, 0.1. So X equals 0.1, so that means the moles of HCl is 0.1. Yep, sorry. Now we have the moles for both of them. Now we're going to do an isotable. So we're not going to focus on H2O because, again, it's a liquid. Okay. Well, we're not going to call this an isotable. Okay. So we added 0.1 of HCl plus, and that's the HCl in the solution. F minus is NaF, and there's 0.25 of it. And remember, there's already 0.25 of HF because it's a buffer. Now we're going to subtract the limiting reagent from the reactant side and add it to the product side. So the limiting reagent in this situation is 0.1 because it's the smaller number. So that means all of the HCl is gone. There's only going to be 0.15 of F minus, and there's going to be 0.35 of HF now. So this is still a buffer. This is still a buffer, so now we're going to use the Henderson-Hasselbalch equation. So pH equals pKa plus log times concentration of the base times concentration of the acid. Now the Ka for HF is 3.5 times 10 to the negative 4. So we do a negative log of that plus the log. The base in this situation is F, so it should be 0.15 over 0.35. So for 29, we should get A. Anybody have any questions? Yeah. So it's going to be 3.19.
So, mine's 6 times.
No questions? Okay.
So it's 3.09.
Yep.
Okay.
Now move on to chapter 18. So I'll give you reaction. We're given the delta H, and we ask for under which conditions the reaction is going to be spontaneous. So in this chapter, there was a chart that summarizes all of this. I would recommend memorizing that chart. So it has the delta S, the delta H, and the delta G. Okay. So the desirable conditions is the delta H being negative and delta S being positive, which means the entropy is going to increase and this reaction is going to release heat. So the delta G is spontaneous at all temps. And when the delta H is positive and the delta S is negative, it's non-spontaneous at all temperatures. All right. Now, when they're both positive, this is only going to be spontaneous at high temperatures. Now, when they're both negative, it's going to be spontaneous only at low temperatures. Okay. So for this one, it's going to be spontaneous when delta S is negative and at low temperatures, so the answer is D. Now 31, yes.
Do you know what the nearest bathroom is?
I imagine if you keep going, there's one right there.
Would you?
Uh-huh. Okay. Now 31 says when liquid freezes, which is true about the signs of enthalpy and entropy. So when liquid freezes, it's going to release heat, so delta H should be negative. I'm going to cross out A and B. And then when it turns from a liquid to a solid, the entropy should also be negative. So 31 is D. Everyone following? Okay. Now 32, looking for which of the following processes have a delta S of greater than 0. So for this, we're going to look at the states of these compounds, and we're going to look at the moles of the gases. So gas have the highest entropy, then liquid, and then solid. So for A, the delta S isn't greater than 0 because you're going from a liquid to a solid. Now for B, the delta S also isn't greater than 0 because you're going from 4 moles of gas to 2. For C, you're going from 2 moles of gas to 4, so delta S is greater than 0 for C. Now it's not greater than 0 for D because you're going from, on the reaction side, you have solid and 2 moles of gas. You're going to only 1 solid, so the entropy decreased. Yes?
Why is number 31?
31?
Yeah.
So you went from a liquid to a solid, that means the delta S must be negative and heat should have been released.
Yeah.
And then the entropy, the delta S, is negative because you're going from a liquid to a solid. So it's not as, so when you go from a liquid to a solid, the particles don't move around as much. Yes?
Okay.
For 30, why is B incorrect?
30. Why is B incorrect? So I gave you a delta S. Wait, I gave you the delta H, and it's negative. And for B, it says a positive delta S, but that says at high temperatures only.
Right, so if the temperature's high, then
but it says at high temperatures only. So when delta H is negative and delta S is positive, it's spontaneous at all temperatures. It doesn't matter what the temperature is. Now we're going to go on to chapter 19. All right. So I gave you an equation, and we're going to balance it in a basic solution. All right. So we're going to find the oxidation states for all of these elements. So the oxidation state for oxygen is pretty much always -2, and there's 4 of them. So that means there's a charge of -8 here, and there's an overall negative charge of -1. So that means Mn should have a charge of +7. Now for N2H4, hydrogen has a charge of +1, and there's 4 of them. So that means nitrogen must have a -2 charge for each. Now for MnO2, oxygen is again -2, and there's 2 of them. And this compound is neutral, so that means Mn must have a +4 charge. Now again for NO, oxygen is -2, that means nitrogen must be +2. So now we're going to split this up into the 2 half reactions. So we have MnO4, MnO2, then we have N2H4 turned into NO. So MnO4 to MnO2 is the reduction half, because Mn went from a +7 to a +4 charge. That means it must have gained electrons. So this is the reduction. So that means this is the oxidation half. So now we're going to balance them. So the reduction half isn't balanced, so we're going to add 2 things of H2O on the left side. No, we're going to add to the right side. All right, now the oxygens are the same amount. Now we're just going to balance the hydrogens. So we're going to add 4H plus to the left. Now because this is basic solution, we need to balance out the hydrogen we just added. So we're going to add 4OH to both sides. And then these 2 OHs are, the OH and the H plus are going to come together, and it's going to create water. Now we're going to balance the bottom one. So we need to multiply this by 2. So nitrogens are exactly the same. And now we're going to add 2 things of H2O to the left. So the amount of oxygens are exactly the same. And now we're going to balance the hydrogens by adding 8 hydrogens. Now we're going to balance the hydrogens by adding 8 OHs. Okay, and that's going to turn into water. All right, now we're going to clean this up. So on the first one, you have H2O on both sides. That means there's not going to be any H2O on the right. There's only going to be 2 H2O on the left. Now for this one, we're going to cross out this H2O. We should only get 6 H2O. So now we're going to write this again.
We have to balance out H minus H plus first, then the OH.
Yes. So you have 4 H2O plus MnO4 Okay, now we need to balance out the electrons. So on the left, there's a -1 charge. On the right, there's a -4 charge. That means you're going to add 3 electrons to the left. Now on the bottom one here, there's a -8 charge, and there's 0 charge on the right. So we're going to add 8 electrons to the right side here. Now we're going to make the electrons, Now we're going to make the electrons cancel out, so we're going to multiply it by a common factor. So we're going to multiply the top one by 8 and the top one by 3. All right, so the electrons are going to cancel out. So you get 32 H2O. So right here, we're going to add the two reactions together, so back into one. So you're going to have 32 H2O plus 8 MnO4 minus plus 24 OH plus 3 and 2H4. And the next part of the then you're also going to have 6 NO plus 18 H2O. Now we're going to clean this up one more time. There's going to be no H2O on this side, and there should be 14 H2O plus 8 MnO4 minus plus, going to clean up the OH. There's going to be no OH on this side, and there should be 8 OH on the right. MnO2 plus 8OH plus. Okay. Now this problem asks for the coefficient of MnO4. Coefficient of MnO4 is 8. Okay, I need a break after doing that one. Yeah. Okay. Now we're going to go to 34. All right. So this says which of these ions is the best reducing agent. So when we look at these, they always give us the reduction half, but when a reaction occurs, it's always the oxidation and reduction occurs. So it means we need to flip one of these so the oxidation happens. So we keep the higher number and we flip the smaller, the one that's closer to 0. So we're going to flip iron. So that means Fe. That means the E of the cell for this one is now plus 0.44. Now this question asks for the best reducing agent. The reducing agent is the one that's going to be oxidized. So we just flipped this equation because we said this is the oxidation half. That means the best reducing agent is Fe. Now for 35, we're just looking for the standard potential of E for this reaction. So again, we're going to flip the smaller number because that's going to be the oxidation. So the smaller number in this one is again iron. So you have 1.61 V, and we're going to flip this so we get 0.44 V. So we're going to add that together. We should get B. Everyone good? Okay.
It's being reduced F. What is the standard electrode potential for this reaction?
Yes. If you do cathode minus anode, that's the same thing as flipping. I believe so. If you do cathode minus anode, you should get the same answer.
So, why do we determine that iron is the best reducing agent?
The reducing agent is the one that's going to be oxidized. So in this situation, Fe is oxidized, so it's the reducing agent.
Fe is being oxidized
Yep.
because it's on the bottom.
Because it has a smaller E cell.
Okay. So oxidation is smaller E cell.
Yep. Okay. Good. Now we're going to go to 36. This is basically the one stoichiometry question I believe you guys need to know for Chem 2. So we're looking for the mass of chromium nitrate. It's going to be plated on an electrode from the electrolysis of a current of 0.5 A for 70 seconds. The first thing we're going to do is write what this reaction looks like. Okay. So chromium 3 nitrate looks like this. And we know it looks like that because nitrate has a -1 charge and it says chromium 3. That means chromium has a +3 charge. So you need 3 nitrates for this to be neutral. So you're going to have chromium nitrate. We don't know how many electrons we're adding yet. When it separates, we get chromium and 3. Okay. That means the oxidation number of chromium here is 0. And so the oxidation number here for this one is +3. That means we're adding 3 electrons here. Now we need to know the amount of electrons when we do the stoichiometry of this next. All right. So we're looking for the mass of chromium nitrate. So we're starting off with 0.5 amperes, and that's what it is. So 0.5 A equals the same amount of C over S. So 0.5 ampere equals 0.5 C over seconds. So you have that. Then we're going to times by the seconds. It's gonna be a long one. Yeah. Times the 70 seconds. So that's going to cancel out. But we still have C. That means we're going to divide it by Faraday's constant. It's 96.485. And so it's 96,485 C over moles. But because we want the C to cancel out, the 96,000 is on the bottom. So you divide, C cancels out. Now you're going to have, so we're going to write. Now you have moles of the electrons. This is where the electron number comes in. So you so we're going to divide it by the 3 mole electrons, and it's 1 mole chromium. So mole electrons cancels out. So then you just have the mole of chromium. So now we're just going to multiply by the molar mass of chromium, which is 52. Times. And then it all crosses out. And all you have left is grams. So you should get 6.28 times 10 to the -3 grams. I give this answer in milligrams, so we're just going to times this by 1,000. So it should be 6.3 milligrams, which is A. Any questions? Yeah. Yes.
Amperes is like C minus S, I mean C over S, yeah?
Yep. That's what it equals.
Okay.
Now we're going to go on to chapter 20. This should be the easiest part of this final, because this nuclear chemistry section is pretty easy. All right. So in this one, we're going to fill in the particle for the following nuclear equation. So we have Br, and it decays with +1 electron. So that means first of all, we change the protons. That means this is not going to be the same element. It's not going to be Br again. So the next part of this, one of these electrons went away. So that means there should be 1 less of 35, which is 34. So the answer is C. So the other half of this is they didn't affect the neutron and proton amount, but there's a +1 here. That means on this right side here, this number right here should be 1 less than 35, which is 34. Okay. Now we're going to 38. So for this one, you just need to know what the definition of a beta decay is. And the beta decay is 0, -1, E. So we go from this compound to a beta decay of this. So that means on the right side, there should be one less at the bottom number, which is A. Now for 39, we're going to fill in the missing particle for this nuclear equation. So for this one, all you need to know is what a gamma decay is. A gamma decay doesn't affect the mass of it at all. It's a less energized state. So that means this compound is exactly the same and just less energized now. So it should be A. Now for 40, I believe this is an alpha decay. So we're just going to look for a compound that has 2 less on the bottom number here, which is B. Any questions? Yep.
Could you bother going over the redox reaction that occurs in a basic solution again?
Okay.
Please. I just want to review.
Okay. Oh, okay. Yes. Is it 4? On the book, does it say it's 4? It's 4. Then it should have been 4 times. That means I should have written body center cube because the body center cube is 2. What number is it? 7? So you didn't get A?
I just want to see like the answer to like the redox reaction.
That.
Okay, thank you.
Mm-hmm.
Have you been studying?
If you guys have any questions? Yep.
Again, for looking at number 40, you said that
40.
the proton number changes, it's not the same element as the center.
Yep.
So that applies for alpha, beta.
All of them. Yep. Because when you change a proton, it's a different element. Like if you look at the periodic table, they all have a different proton number because it changes to a different element now. No questions? I can go over whatever you guys want. Yes. For number 7.
Can we please go over number 7?
Where did I? Interesting. Don't know where I wrote that. Just gonna go here. So for number 7, we need the molar mass of nickel, and we're going to divide it by Avogadro's number, and then we're going to times it by the atoms per unit cell.
Okay, like, is there like an equation? Did you give the equation for that or no? Nickel.
So molar mass divided by Avogadro's number is in grams. Is that the equation you're talking about?
Yeah, molar mass of nickel.
Don't remember what the molar mass. What did I say the molar mass of nickel is? What did I say the molar mass of nickel was? 58.7.
58.7 grams divided by like atoms, right?
Yep, divided by Avogadro number, which is 6.022 times 10 to the 23.
Yes.
Yep, times it by 2, and that should give you the grams.
Doesn't face-centered cubic have like 4 atoms per unit cell?
Yes, it should have said body-centered cubic then.
So it's body-centered. It's a body-centered cubic then?
Mm-hmm.
Okay.
I have 30 more minutes. And I have to keep going. Number 8. Number 8 has to do with solubility. So we increase the temperature of the solution, and in the solution we have a gas and a solid. So the solubility of solid increases as the temperature increases, but the solubility of a gas decreases as the solution increases. So that's why when we warm this solution, the carbon dioxide is going to bubble out, which is the same thing as the solubility decreasing. Good?
So what is the mass of 1 unit cell? We then per mole, and then we times it by like 2, right? Like 2.
Real quick. There's a survey, I guess you guys have to fill out.
What is it again? Like 2 atoms per mole or something?
There's just one sheet, I guess.
So it's 2 atoms per mole. Okay.
I imagine everyone that has a test today already left, which makes sense. There's 2 in there. Yeah. Number what? 5? Okay. This, it says bubble and number provided by the whatever. Number is 55. 55. Okay, he said you want to go over number 5, right? Okay.
Yes, please.
Number 5. Okay. All right. Number 5. Oh, is it because you got 7.1? Did you do it? Did you get it?
I did wrote it down.
Oh, okay. All right, so the equation for this problem is Q equals MCAT. So basically just figuring out the amount of heat added to this solution. And we have everything we need to figure that out for water. And we need specific heat for platinum. So we basically write in MCAT twice. I think you give it to me. You nod no? Thanks. Good luck on your final.
Thank you.
All right. So the mass for water is 130. Specific heat for water is 4.184. Change in temperature for water is 27. And then the mass of platinum is 62. We're looking for the specific heat, and the change in temperature for that one is 27? No. For that one it's 33. Thanks. All right.
Here we go.
Thank you. Multiply the left side, you get 14,685.84. And it equals 62 times. All right, so you get 2,046 C. So you should divide. Now I get 0.7, like my answer key said. Interesting. So it's 0.7. I swear when I do this in my calculator I get 0.7, which is annoying.
I got 7.17-ish.
Gonna go with you guys. It's 7.1. All right, so 7.1.
7.1.
Yeah. All right.
Can you please go over number 3, please? Like, why is it that Q equals moles times heat of vaporization?
Why?
Yes.
Because those are the variables we were given? I'm not sure.
From like the melting diagram of water.
Yeah.
So it goes like.
So we're looking for Q. We're given the delta H, and we can find the moles because we're given the mass.
Okay. So like warming up the slanted ones, and then it's transitioning.
You guys want me to go over like a titration question?
Transition.
Yes?
Yeah.
I can make one up. All right. All right. I'm going to do strong acid and strong base, or weak and then a strong? Either or? I'll do both. We're going to have time.
Well, please.
Yeah, we're going to have time to do both. Okay.
You have
Yes,
time,
sir.
right?
Yeah, I don't. This isn't over till 9:30, so we got 28 minutes. So we're going to say we have let's say the molarity is 1 and the liters is 0.2 of HCl. Wait. Yeah, we do both strong right now. And we're going to say concentration is also 1. The liters is 0.14 NaOH. So we're going to titrate HCl with NaOH. The first thing we do when we have these problems, we identify if it's strong or weak. HCl, strong acid. NaOH, strong base. The next part is we're going to find the moles of each of these. So we have concentration of, so molarity equals moles over liters. So you have 1 equals, moles what we're looking for, 0.2 liters. So we're just going to do 0.2 times 1. So the moles equals 0.2 for HCl. Now we do the same thing for NaOH, and we should get 0.1 moles. All right, now I have the moles for both of them, and we're going to write out what the equation looks like. Mm-hmm. Yeah, you could change it to moles. I believe so. Thank you.
Millimoles is like 1,000 moles, right?
Yes.
Okay.
Okay, we have the moles, now we're going to write the equation. So we have HCl. The Cl is pH neutral, so we're just going to write. Oh, yeah, sorry. All right. So we have H3O plus NaOH, and Na is also pH neutral, so we're going to do plus OH. And that's going to create 2 things of water. But because water is a liquid, we don't have to look at that section. All right. Now we said there is 0.2 moles of HCl. That means it's 0.2 H3O plus. And there's 0.1 moles of NaOH, so there's 0.1 here. Now we're going to subtract by the limiting reactant, which in this situation is 0.1. So you minus both sides by 0.1. You have no more of the base, only have 0.1 of the acid left over. So now what we go for from here is we're going to find the new molarity. So because you went from 0.2 liters to 0.1 liters, that means the concentration has changed because there's a new volume. So molarity equals moles over liters. We said the moles is 0.1. The liters of HCl is 0.2, and the liters of NaOH is 0.1. So then you're just going to get 0.1 divided by 0.3. So you should get the new concentration is 0.33. Now from here, we should do the negative log, and we should have the new pH of the solution. So we should get, the pH is 0.48. Okay. All right. Now we can do 1 weak and 1 strong. So let's say,
Is this like after the addition of what?
what?
For the titration problem?
This one right here?
Yeah. What's the addition
The NaOH.
after an addition?
Add NaOH.
After addition of how many moles of NaOH?
Right here, 0.1. That's what we found out already.
After addition of 0.1 L NaOH, right?
Yep.
Okay.
Okay. Now we're going to do 1 weak, 1 strong. So let's say the concentration is 0.3. We have 100 milliliters of HF. Now the concentration for this base is going to be 0.4 m, 100 milliliters. We're going to do NaOH again. So HF is a weak acid. NaOH is a strong base. So again, we're going to find the moles for each of these. So we're going to have 0.3 equals X over 100 mil, that should be 0.1 liters. Yep. There we go. So I can do 0.1 times 0.3. So the moles equals 0.03 for HF. And then the moles for NaOH should be 0.04. All right. Now the next part we're going to do is going to write the equation. So we have HF plus NaOH, and we're not going to write the Na because it's pH neutral. And that creates water and F. All right. So we said in this solution we have 0.03 moles of HF, we have 0.04 moles of NaOH, we have 0 moles of F minus right now. Now we're going to subtract by the limiting reagent. So minus 0.03 minus 0.03. So you have no more of this weak acid. We have 0.01 of this base, of this strong base, and now we're going to have 0.03 of F minus. So now you have a strong base, and you have F minus, which is a weak base. But because weak bases only weakly create OH ions, we're only going to focus on this OH here, because it's going to create way more OH than the F is going to create. So what we're going to do now is we're going to find the new concentration. So again, M equals moles over liters. We said the moles of NaOH is 0.01. We have 0.01. And the new liters is, so it's 0.1 plus 0.1. So you get 0.01 divided by 0.2. So the concentration is 0.05.
How come we get like 0.1 plus 0.1 or like added liters?
So we had 100 milliliters of this weak acid, 100 milliliters of the strong base.
Oh,
So you have a concentration of the NaOH, and now we're going to find the pH by doing the negative log. So negative log of 0.05 is going to give us a pOH. So I get 1.3. Now I'm going to do 14 minus this to get the pH. 12.69. That's the pH. Thanks. All right, what do you guys want me to do next? A buffer one? All right. Do I have more paper? Went through way more paper than I thought I would. To the back of this. All right. So let's say, all right, this is going to be a 1 liter buffer solution. Oh, thanks.
Thank you.
All right, so we're going to say a 1 liter buffer solution. We're going to say the concentration is 0.2. We use the same buffers as before, so HF and 0.2 M. NaF. All right. Now we're going to add 0.1 M at 100 milliliters of let's do NaOH again. All right. So NaOH is a strong base. Bases act with acids. That means this NaOH is going to react with HF. So we're going to write what the equation looks like. So you have HF plus the NaOH, and that's going to create water and F minus. All right, now we're going to find the moles for each of these. Because concentration is 0.2 and the liter is 1, that means the moles of HF is also 0.2. Now for NaOH, we have 0.1 equals also 0.1. So the moles of this one should be 0.01. Yeah. All right. So now you have the moles for both of them. Now we're going to fill in the chart. Yes?
For the moles of NaOH,
Mm-hmm.
we have to determine the thing, right?
What?
It's if we divide or multiply, we just ignore the NaF, right? Do we ignore the NaF?
NaF is the same thing as this F right here, so we're going to need it.
Oh, okay.
All right. So we have 0.2 moles of HF. We have 0.01 moles of OH. And we have 0.2 of F in here. So this F is the same thing as NaF, because Na is also pH neutral. All right. So now we're going to subtract the limiting reagent to the reactant side and add that same number to the product side. So the limiting reagent is 0.01. That means there's no more of that base we just added. There's 0.19. Yeah. And there's 0.21 of F now. So this is still a buffer. So we're going to use the Henderson-Hasselbalch again. So pH equals pKa plus log of base over acid. So I use the same buffer I gave you before, so we have the same pK. We have the pKa here already. So the Ka for HF is 3.5 times 10 to the negative 4. All right, so we have that, and then plus log of the base. The base is F, so we're going to have 0.2 over the acid, which is 0.19. So we get 3.4559 log of 0.21. So we're going to add 0.043. So you get 3.499. pH didn't change a lot because we didn't add a lot of this base right here. All right, anything else you guys want to go over?
So it's 3.499. Okay. I don't think so. I really need to review the buffer solutions and everything because I'm scared for this final.
Don't be scared. This study guide I made wasn't too bad, right? And I took more than half these from the ACS book, so.
Okay. This is what we usually find on the ACS.
Yes, they should be similar to these questions that I gave you guys.
Okay. Gotta review my ACS book then.
I have to keep going for 12 more minutes. You guys want me to go over the electrolytic cell?
The electrolytic cell,
Yeah, probably.
I could do that. Okay.
If it's the smaller E cell, it has stronger oxidation.
So you want me to draw this structure out and everything? I could do that.
Yeah.
All right.
Yeah. So if it's oxidized, that means it has a smaller E cell, right?
Yep. All right. So I've broken so much lead. Okay.
I didn't know that.
Yes, we have. Okay. To the electrolytic cell. I didn't draw that fat enough. Okay. So this right here, these are the two electrodes. So electrode is either going to be an anode or a cathode. I like to do the anode on the left.
Electrons flow from the cathode to the anode?
I believe so.
Yeah.
All right. So what I use to remember where oxidation and reduction occurs is red cat. Red being reduction. And then cat being the cathode part. So that means reduction occurs in this half. And another thing, it's anox. So oxidation occurs at the anode.
Okay.
So let's say we use Ag and Fe like I gave. All right. Yeah. Ag. And when they give you one of these, they should probably will be given in the same reaction half. So we're just going to flip this one because here it has the smaller U cell. So I'm flipping the Fe part. So it should be Fe. Now to make the electrons equal, you would times this one by 2. So this whole reaction in one line looks like 2Ag plus Fe turns into Fe2 plus Ag, 2Ag. Okay. So when they give you a problem like this, they'll probably give you this line right here.
I'm nervous.
All right.
I'm really nervous, Mom.
Don't be nervous. All right, so we said reduction occurs in the cathode half. So that means the electrons are gonna, well, let's label. All right. So we said we flip the iron, so iron is the oxidation half. And that means this Ag is the reduction half. Now this solid portion right here is when these elements aren't, they don't have any charges. So because reduction occurs in this cathode right here is the Ag solid. And then there's Ag plus right here in this liquid. So on this side, there's the solid Fe here, and the Fe2 plus is the liquid. All right. So electrons go from anode to cathode because reduction occurs at the cathode. So that means the electrons are going to flow this way in this situation. So that's like a plus. All right. So because the electrons are flowing this way, the anode is going to get smaller because it's losing weight because the electrons from this Fe are going off into this half. So as the reaction goes on, anode loses weight. And the cathode gains weight. So this anode is going to get smaller. The cathode is going to get bigger. So when you have a problem like this, they'll probably give you the equation, and they'll give you examples of this, and you're going to have to label what is what. Another question they could ask is the cell notation. So cell notation is electrode, electrolyte, electrolyte, and then electrode again. All right. So again, we said this electrode is the solid portion here. So that means at the ends should always be the solid elements, and in the middle should be the elements that have a charge on them. On the left side is always going to be the anode, and the right side is the cathode. So that means for this reaction right here, it looks like
So the oxidation is going to be on the left, and the oxidized will be on the left, and reduced shall be on the right. Yes.
mm-hmm. If it's all in aqueous, one of them isn't solid. Is that what you're asking? Yeah. So, and this one right here, both of these are solid. However, there are times where when it's reduced or oxidized, it has no solid form. So that means you have to add platinum because the solid portion is the electrodes. So you need something solid for the elements to hold on to. So the cell notation would have platinum at the end, and then we would have the, yeah.
So you said you add platinum at the top solid?
Yeah, so one of these are going to be aqueous at both times, so then you have to add platinum.
Platinum if they're both aqueous, yes?
Yes, for one of the elements, they have no solid portion.
Only if both are aqueous?
Yes.
Okay.
They both have bases or just one of them?
Like, one set of the element is aqueous. Yes, one set, both of them are aqueous. All right, any more questions?
What about the minus G, R, L, and K? Is the R like 0.08206, or is it the other one?
I believe it's the bigger one. But yeah, so good luck on the ACS final. I say at this point, if you don't know how to do it, I would not learn it because it's only 40 questions.
Okay. But our professor includes 10 of his own.
Mm-hmm.
I'm scared.
No problem.
Thank you so much, Imani.
Yep.
All right. If I pass, I'll tell you, okay?
Okay.
What's the best way to contact you?
Don't need to do that. It's okay.
If I pass, I'm gonna be so happy. Because I want to pass. I'll be so upset if I have to repeat this class again. I only want to do it once and then I'm done, okay?
Why 26?
26. Yes, but it's strontium. See how it makes, you see there's 2 OH here? That means for each time this thing reacts in water, it creates 2 OH. So like, this would look like,
So this is based off the majority of the ACS questions?
yes.
Okay.
So when it dissociates, it's going to create 2 OHs. So you multiply this concentration by 2, so you have the amount of OH that it creates each time. So when you do 0.3 times 2, you should get 0.6. You only do negative log of 0.6.
So you do that with every strong second group from there?
Yep.
So we multiply it by 2 if it's 2 OH.
Mm-hmm.
Okay. So that equals 13.8, which is the answer, yeah?
Mm-hmm.
Okay. Thank you so much, Imani.
Yep.
Temperature is the only thing that will affect the equilibrium constant.
Mm-hmm.
Because
It is basically 9:30, so you guys can go.
right?
Mm-hmm.
And if it's exothermic, changing the temperature either way will make it shift more left or right, right?
Left. Uh-huh.
What?
Mm-hmm. Whatever the problem says, yeah. All right, so it's 9:30 now.
Well, Imani, it's been wonderful having you as a tutor.
Mm-hmm.
And it'll go in like the direction of the reactants if the temperature increases. It's exothermic, yeah? If the temperature decreases, it'll go in the direction of the products, yeah?
Mm-hmm.
Okay. Thank you so much, Imani.
Yep.
Therefore, it'll create more products, yeah?
Mm-hmm.
Okay, thank you so much.
Mm-hmm.
If I get 100 on this final, you're going to tell everybody I was your favorite student.
100.
If I get 100.
You can get 100. I could believe that. You did it twice.
No, so
Someone else has left it.
So
Okay.
if I get 100, you're going to tell everybody I was your favorite, right?
Guess so.
I'm applying to be a start tutor next semester.
Oh,
for
for real?
biology, so I may see you.
Oh yeah, because one of them is leaving. So.